それでは時間になりましたので、環境触媒化学特論1の第9回かな、はい、を始めます。準備しますので少しお待ちください。はい、第9回です。だいぶ来ましたね。はい。これまで光触媒反応の、熱力学と速度論やってきました。それで、今日はちょっと最初に速度論の話をしてから、作用スペクトル、アクションスペクトルムアナリシスの話をします。I will talk about the part 1 of action spectrum after interpreting the concept of kinetics of photocatalysis, but not limited to photocatalysis. So, the same format. Within 72 hours after this lecture, please send email. Today, June 16, so therefore the subject and the first line of mail body should be PC20220616- your student number. So, this is the very, very conventional kinetics of photocatalysis, but not limited to photocatalysis. In the ordinary liquid phase or gas phase reaction, the reaction rate is decreased depending on the concentration in solution or gas phase. In that case, the kinetics is called first order kinetics. That is, the rate is proportional to the concentration. And in that case, here, as you see, the relation between the logarithm of concentration is proportional to, not proportional, and linearly increased with time. So this is the first order kinetics. And please understand, so if the reaction rate obeys first order kinetics, this plot can be obtained. And the reversed relation, if you obtain this relation, this doesn't say that is first order kinetics, as I told you before. That is in two possible cases in photocatalysis. If the adsorption equilibrium is in like Henry type adsorption, that is, the amount of adsorption is linearly increased with concentration in solution or gas phase. In that case, that is not a first order kinetics. That is just the surface concentration is linearly increased with concentration in solution. So therefore, the same plot can be obtained in this case. The reaction rate, the concentration is linearly changed with time. So even if this is not first order kinetics, that can. And also, if the non-equilibrium, so adsorption cannot be equilibrium because the rate of reaction is very fast, or the amount of surface adsorption is very, very small. In that case, the surface concentration is always zero. So therefore, the rate of reaction is the rate of substrate diffused to the surface. In that case, the same plot like this is obtained, even if this is not the first order kinetics. So, and to distinguish which is which, so it is necessary to check the right intensity dependence, because in the latter case, no right intensity is included in the reaction rate equation. But for the surface ND type surface adsorption case, the reaction rate is proportional to right intensity. So therefore, it is possible to distinguish which is the reason for that. So again, so this is just the reaction, the results obeys the assumption. And so many attendees, students, said that that is the first time to learn about the fixed law of diffusion. And this is very simple and very, how to say, clear equation, fixed law, and like Langmuir adsorption isosound. So therefore, it is possible to understand very, very clearly. And you can find this, so the textbook in physical chemistry also contains those interpretations of the fixed law. And anyway, the important point is when we analyze the rate of reaction to rationalize, to say that is suitable, it is the linearization method is used. So that is, this is also linearization to make, if the proposed kinetic equation obeys, the real actual experimental results obey the kinetic equation. In that case, the linearization is very, very clear. So now computer analysis can reproduce the results like this, not make such a linearization. But before that, when I was a graduate student, in that case, no computer simulation cannot be made. So therefore, it is necessary to make the section paper in Japanese, hoganshi. And it is possible to see, to check that is linear or not, very easy. So therefore, every time we make analysis for linearization, that is very important point. And anyway, so the linearization, choksen kinji in Japanese, to make the equation derived into this form, the y equal ax plus b. So in Japanese, a is katamuki, slope, and b is y-intercept, y-seppen. So plotting x and y. Y is the real reaction rate or something, and x is some parameter, for example, the concentration or something, but not directly obtained such a linear equation. So therefore, it is necessary to derive the equation into this type of form. Anyway, this tells that the only showing the consistency with theoretical equation, but not excluding the other possibilities. This is very important point. For in kinetics, so every time we prepare, think what is the theoretical equation showing that reproduce the results of reaction rate. But that is a necessary condition, and therefore it is impossible to exclude the other possibilities. So again, when we make the linearization and these two, and also the conventional first order kinetics, they obeys this linearization. So that is something is the logarithm, in this case, the logarithm of concentration is plotted against the time. So this linear relation tells this first order kinetics can be, and this process can be, and this process can be. So it is impossible to decide which is the most appropriate results. So that is it. So anytime the kinetic analysis is just assumption and impossible to exclude the other possibilities. 速度論解析というのは速度式を立てて、そしてそれを直線近似の形に変換して、で実際のデータを当てはめるということです。で、結果として、例えばこういうプロットが出てきた濃度の対数を時間に対してプロットしたら直線になったとしても、これはいわゆる普通のコンベンショナルな一次反応速度式に従っている。そこと矛盾はしない。矛盾しないけど、こういうプロセスであると考えても矛盾しないし、こういう拡散立則になっているんだと考えても矛盾しない。だから直線近似が得られた、それが、思った通りのものが得られたとしても、それは一応間違いではないということを示しているだけで、それだけです。それ以外のことは何も示していない。他の可能性を除外できるわけではない。そうすると、もっと別の実験をやって、他の可能性を除外できるかどうかっていうのをチェックするということをやっていくわけです。でそのthen the linearization. So, はい。The photocatalytic reaction rate R equal I phi KEHS over KHS plus KR. So, the S is amount, assuming that S is amount of adsorption, and K is equilibrium constant, and C is concentration in solution. And therefore, by inputting S value into the first equation R, the R can be something like this. So, and this is not a linear relation. So therefore, to make it linear, the R reciprocal R, 1 over R, is plotted against reciprocal C, 1 over C. So how much is the slope and y-intercept, please? 反応速度式が R イコール、ちょっと複雑な式ですけど、C がいっぱいいろんなところに入っていると。で、これだと直線近似できないので、直線近似にするために R 分の1っていうのを考えたときに、ひょっとするとそれを C 分の1に対してプロットすると直線近似できるかもしれません。ということになります。この分数式見たら、分子の方は項目は一つで、分母の方はプラスでこうつながってますから、分子で割ってやればなんかできそうっていうのは、分母分子を逆にすればできそうっていうのはできると思います。はい。この白枠の中に、y 切片とスロープいくらになるでしょう。どうぞ。 はい。こうなりますね。ちょっと複雑だけど、いずれにしても R 分の1が C 分の1かける傾きと定数に分かれている。この今入れてもらったものは全部定数になりますから、変わっている C は変化している、R は変化しているんですけど、他の部分変わってないということになります。So it is possible to make a linear relation between 1 over R and 1 over C. So it is possible to plot R reciprocal R against reciprocal C. So then it is possible to say something about the linear relation. So if the reaction A to B is expressed using K like this, so A must be concentration of reaction. So, but in this case, this is the conventional one. But in solution, that is that A must be a actual concentration. But for example, enzymatic reaction, the A actual concentration must be EA. That is the complex of enzyme and the reaction substrate. And for surface reaction, A must be A on the surface, adsorbed amount on the surface. So it is possible to make any characteristics. It is possible to use this equation, but this is just a necessary condition. So then the Langmuir adsorption. So then this is catalysis, shock by hand, not photocatalysis. In the ordinary catalytic reaction without using photoirradiation. Sometimes, not all the cases, sometimes the reaction rate is proportional to the surface concentration, and small k, the first term, is kinetic constant, rate constant. Okay, so in that case, R reciprocal R can be shown like this. So this is the ordinary plot for adsorption induced catalytic reaction. これは触媒反応、光触媒反応じゃない。触媒反応で、触媒反応が表面の吸着量に、速度が表面の吸着量に比例すると。すると、SKC オーバー1プラス KC っていうのはラングミア式で表される吸着量ですから、それにスモール k、速度定数をかけたものが速度になります。でもこれはその分母と分子 C が入ってて、直接、直線化できないので、例えば R 分の1をこういう形で表すというと、こういうプロットができるというわけです。However, this is the linearization to make this the top equation into linear form. There is not only way, not one way. So the other possibilities, and that is this one. So C over R is plotted against C, not reciprocal C. The similar linear relation can be. So, okay, so not limited to this type. So almost all the people use this type of plot for to check the Langmuir adsorption induced surface reaction mechanism. So that is the reaction rate is the reaction of substrate on the surface. So this is true. But the linearization, there are two ways of linearization like this. And actually, the same, the meaning the same. However, in this case, the reaction rate, reciprocal reaction rate, 1 over R is plotted against 1 over C. So therefore, this point is the most low concentration part. And for low concentration reaction, that might be the measurement of reaction rate or concentration itself. That has some large error compared with high concentration part. So therefore, this data, the highest data, have some errors. But if the such a linearization is used, in that case, the reaction rate C over R is plotted against C. So therefore, the highest point has the lowest error. So probably to check the slope and these are the ideal plot. So therefore, this is completely linear, but the plot has some deviation. So therefore, it is necessary to choose at least which plot is better for the experimental results analysis. 直線化はもうほとんど 100% って言ってもいいほど論文ではこういう近似をするんですけど、この場合 C 分の1を取ってますから、一番データが大きい。これがかなりここが変わるとスロープかなり変わるわけですね。で、この誤差大きいわけです。この誤差大きいのが決め手になっちゃってる可能性が高い。だけど、こっちのプロットを使うと、C に対してプロットしますから、濃度が高いということが、誤差が少ないとするならば、こちらの方がスロープの信用性が高いということになります。で、このあたり、かなりその判断が難しいところで、どっちがいいのかっていうのは難しいです。そんな簡単には決められません。なので、そこはちゃんと考えていかないといけないし、やっぱりその現実の実験の場合には誤差が必ずあるんだということを考えないといけない。で、それに、これ2つ、今例出してますけど、別にこの2つだけじゃなくて、いくつでもその直線近似、直線化することは可能なわけで、だからそこのところの判断っていうのは、いつもこれを使うんだと決まってるわけではないということを覚えておいた方がいいです。はい。で、これがラングミア式の、触媒反応の場合ですね。ところが、それで、触媒反応の場合、今のをラングミア・ヒンシェルドメカニズムだっていう人も、光触媒の分野ではいるんですけど、それは間違いです。で、the true reason, probably this is the first time for you to hear this Langmuir Hinshelwood mechanism, but that is very famous mechanism. And this is limited to bimolecular reaction, that is two kinds of substrate react on the surface. And both of these are adsorbed on the surface. The adsorption site is common to substrate A and B. The same reaction site can, adsorption site can adsorb A or B, but different equilibrium constant because depending on the substrate, the power or ability of adsorption is different, even if the same adsorption site is assumed. And then you can derive the equation for Langmuir Hinshelwood mechanism. So that is the multiplying the concentration A on the surface and concentration B on the surface. By multiplying these two, this is proportional to the reaction rate. Okay, so I think it's possible you can derive the equation for Langmuir-Hinshelwood mechanism that is two kinds of substrate react on the surface. はい。どうぞ。ここにリアクションレート R イコール式が出てきます。その中には KA、KB、レートコンスタント、ごめんなさい。これは吸着の平行定数。AB のそれぞれ。それから、リアクションサイトの飽和量ですね、S。そして、共通というか、一つのレートコンスタント。K、スモール K。で、assuming the bulk concentration A and B, CACB, respectively, rate R is proportional to surface concentration A and B. And then you can obtain the rate equation. So please think for a while. 3 minutes.はい、できましたか？こんな感じ。よく似てるんですけど、共通のサイト。So the adsorption site is common. So therefore, this part, KACA plus KBCB. So in the ordinary Langmuir adsorption, only 1 plus KC, but the plus KACA plus KBCB. And the top part is KACA KBCB and S square and constant. So this is the relation of reaction rate in catalysis, not photocatalysis, the bimolecular reaction. And why such a Langmuir-Hinshelwood mechanism is proposed? That is another type of mechanism is also proposed. That is ED-DD mechanism. So that is also bimolecular reaction of two substrates, A and B. And the difference from Langmuir-Hinshelwood mechanism is A is adsorbed on the surface, but B is not adsorbed. The B attack A on the surface. So therefore, they are a bit different. And in that case, how is the reaction rate like Langmuir-Hinshelwood? This is Langmuir-Hinshelwood type mechanism. The similar but different rate can be shown for this ED-DD mechanism. So please. So reaction rate is proportional to the surface concentration of A and the concentration of B in solution or gas phase. Pan-san, please mute your microphone.ただいま16名。だんだん減ってきたね、出席者に。まあ、YouTube で見てもらったらいいんですけど。はい。こうなります。簡単ですね。A の方は吸着量ですから、1プラス KCA 分の KCA、SKCA。これが A の吸着量。で、B の方は、もう直接それが作用しますから、ここに分子の方に CB が。で、レートコンスタント K が入る。So, in this case, only A is adsorbed on the surface. So, therefore, one SKACA over 1 plus KACA. This part is concentration of A on the surface. And the CB attack this A on the surface. So therefore, the reaction rate is proportional to concentration of B. And the K is rate constant. So many discussions, so many proposals of this ED-DD mechanism, but actually almost no case such a. So at least in my knowledge, not practically not so many reaction obeys this ED-DD mechanism. And again, even if the reaction rate can be reproduced by using this equation, but this is only the necessary condition. Another mechanism can interpret, may interpret. ED-DD機構っていうのは昔から言われてるんですけど、少なくとも私が知る限り、ED-DD機構で触媒反応、光触媒反応じゃないですか。触媒反応が進んでるっていう例は、でもないみたいだし、もしこの式で反応速度が再現できたとしても、先ほどから言ってるように、これは単に必要条件。ED-DD機構だったら、このメカニズム、この式になるはずだって言ってるだけで、他の反応機構が同じような関係式を出すかっていうと、それは分からないですね。はい。で、 going back to photocatalysis, the first order kinetics for substrate, if there is something, the reaction gives the first order kinetics, that is reaction rate, the concentration, logarithm of concentration is linearly changed depending on time. So that is first order kinetics. But actually, in photocatalysis, not such a the conventional first order reaction happens. And to check this is the two possibilities, adsorption equilibrium during the reaction in Henry fashion over low concentration part of Langmuir fashion. And the other part is not non-equilibrium of adsorption due to the faster consumption of substrate on the surface. That is, the surface concentration is zero, and the diffusion limited process. And to distinguish the possibility among these two, this is possible. And then the reciprocal reaction relation between with concentration and substrate. That is so many examples. That is possible, and linearization. So the linearization for catalysis, that is the surface concentration, can be shown by like this. So therefore, R reciprocal R can be linearly changed depending on the 1/C reciprocal C. Yes, and in photocatalysis can be the similar equation can be. So therefore, 1/R can be linearly changed by 1/C. 触媒反応でランゴミア吸着を仮定すると、R 分の1と C 分の1が直線関係。だけど、光触媒反応で同じように考えたら、R 分の1と C 分の1のこういう直線関係が得られるはずだ。だけど、例えば、Y インターセクトとスロープが出てくるんですけど、それの比ですね。The ratio of Y intersect and slope for catalytic reaction, that is just equilibrium concentration. But by checking this equation, the ratio of y-intercept and slope in photocatalysis, that is a bit complicated. Not only equilibrium constant, adsorption equilibrium constant, those parameters are also included. 触媒反応を考えても、光触媒反応を考えても、R 分の1が C 分の1で直線的に変化するってことはあり得るんですけど、あり得るっていうだけで、それで得られたプロットの Y 切片を傾きで割ったものっていうのは、キャタリシスの場合には、単純に吸着の平行定数ということになるんですけど、フォトキャタリティックリアクションの場合はその単純なものじゃなくて、ちょっと複雑な式になる。だから常になんかそういうのがうまく得られるわけではなくて、これしかわからないですね。これしかわからない。で、フォトキャタリティック、今の式から言うと、フォトキャタリティックアクティビティをリアクションレートだと、こういう形の式になってるわけですね。で、そうすると、C っていうのは、あるいは I ですね。これ、実験条件ですよね。光触媒そのものの性質ではないわけですね。で、S は確かに、なんて言ったらいいのか。プロパティなんですけど、でもこれ光触媒でなくてもあるプロパティですよね。で、ここの部分だけですね。KEH、KR。KEH っていうのは、電子と正孔が何か基質と反応するときの素過程の速度定数。KR はリコンビネーション 再結合。で、おそらくこれだけが光触媒としての性質ですよ。それ以外は光触媒じゃない。So, assuming the photocatalytic activity, so that is the reaction rate is shown like this in the most simplified form. And here, C and I is a flux, photon flux. The C is concentration in solution. That is outer parameter, not property of photocatalysis. That is a reaction condition and can be adjusted freely. And S is the saturated adsorption, saturated density of adsorption site. And the K is adsorption equilibrium constant. And I is photoabsorption efficiency. So that is the photocatalyst solid property. This is true. But that is extrinsic ability for photocatalysis because not for photocatalytic reaction, the S, I, and K can be determined. And only this part, KEHKR, this is the rate constant for electron hole reaction and recombination of electron hole. And this is intrinsic ability. And the important point is, can we measure KEHKR from experimental results or not? And you need to answer this question. That is no. Every time, KEH and KR is KEH over KR appears in this form. So it is impossible to divide. Every time what we can see is a ratio of KEH and KR and no real constant, rate constant of those steps because it is true because it is impossible to see those reaction KEH the electron hole reaction and recombination independently. So therefore, it is impossible to determine the absolute value of rate constant KEH and KR. Every time what we can see is a ratio KEH over KR. KEH、KR が光触媒の能力とも言えるんですけど、それをそれぞれ別々に出せるのかというと出せなくて、これが良かったとしても、つまりこの KEH オーバー KR の値が大きい、つまり反応性が高いとしても、それが KEH が高いのか、KR が低いのか、小さいのか。どっちかわからないですね。なので、分離できない。一生分離できない。誰も分離できない。ということを誰も気がついてないと言ってもいいかもしれません。はい。そこがポイントですね。で、もう一遍戻ると、フォトキャタリシス、もうちょっと非常に複雑な式ですね。で、これを直線近似したら、こうなります。で、だけど、ここで K っていうのは、ちょっと複雑な式になってるね。さっき言った、この比が入って。So it is possible to linearize this complicated rate like this. But by assuming K equal I phi KEH over KR, it is possible to make the simplified linear relation. And both these two plots show the results. Yes. And can we measure directly? So actually, it is impossible. So every time what we can obtain from the y-intercept and the slope, every time what we can know is the large k can be. But it is impossible to determine KEH and KR independently. はい。さっきの話と同じなんですけど、直線近似にしてやったら、実験データから y 切片と傾きを求めることができるんですけど、そこから、ラージ K は求めることができるかもしれません。だけど、それ S が分かるんですけど、だけど、この非 KEHKR は常に非としてしか表せないというわけです。で、そこがやっぱり問題かなと思います。もう一遍戻って、我々はよく光触媒活性って言うんですけど、それは何を見てるのかって言ったら R なんですよね。速度を見てる。速度が速ければ活性高いってことになるんですけど、でも I とか C が大きくてもやっぱり速度が高くなる。でもそれは光触媒の能力じゃないですよ。それから、拡散立則の時みたいに、この、S が大きければ反応速度が速くなるんですけど、別にそれ光触媒としての性質じゃないですよね。ただ、非表面積が高いっていうだけで。S とか K とか φ とかいうのは光触媒としての性質というより材料の性質なので、活性なのかって言われるとちょっと難しいと思います。本当は KEH がより大きく KR がより小さいのがいいんだけども、それを分離して求めることは現実的には不可能。こういう比だろうって思ってるだけだって言われるんですね。で、ここまで分離して KEH、KR まで出してきてこれが大きいんだっていうようなことを議論している例はないです。でそれで光触媒活性って言っても、ひょっとしたら前回から言ってるように、拡散立則の場合だったら、もうこんなん関係ないわけですね。KEH、KR なんか関係なくて、ただ S が大きければ反応速度が速くなるっていうわけですから、それが本当に光触媒活性かって言われるとちょっと難しい。So, photocatalytic activity in almost all the cases, including ours, they evaluated by reaction rate. But the reaction rate contains several parameters, and for example, C and I is not the property of photocatalyst, and SK phi, that is the property of photocatalyst, but that is not directly related to photocatalytic reaction itself. And what we have to see is the KEH and the KR. But actually, it is impossible, very difficult to even extract KEH, KR part only. And even if we can obtain KEH and KR, it is impossible to separate KEH and KR. この辺がもう限界です。This is the limitation of photocatalytic reaction study in photocatalysis. はい。で、ちょっと今の式に関係あるんですけど、I で光が入ってきて、で、phi で吸収する。で、ここがあんまり着目されてない。So, not so many researchers in the field of photocatalysis focus on I and phi part. That is neglected. So, we focus on this I phi part. And that is action spectrum analysis. In Japanese, 作用スペクトル解析。So, for example, the practical application of photocatalysis, the superhydrophilicity and oxidative decomposition of organic and inorganic compounds. Yes, and that is that proceed through the first one is the photoabsorption, as I told you before. And then that produces electron and hole pair, and that is used for reaction or recombination. That is no reaction happen. So therefore, this part, photoabsorption part, is very important to determine the concentration of electron and positive hole pairs in photocatalysis. And therefore, in those principles, it is necessary to say that the reaction must be, the necessary condition of photocatalysis is reaction must be initiated by photoabsorption of polycarbons. That is natural. But it is a bit difficult to say really the photoabsorption of photocatalyst initiates the photocatalytic reaction. Okay, so when I start the work in photocatalysis as a PhD course student in 1981, at that time already generally accepted concept that is Planck test of photocatalysis. The co-presence of three requisite photoirradiation photocatalyst, that is solid material, and the reaction substrate. The three requisite co-presence is indispensable. That is Planck test. 私が博士課程で光触媒反応の研究を始めたとき、もうすでにプランクテストという概念があって、光照射、光触媒と思われる固体物質と反応物質、この3つのいずれが欠けても反応が起こらないということをチェックする必要がある。これ正しかったら正しかった。間違いじゃないです。これは necessary condition. So this is the necessary condition. Necessary condition. If the reaction is initiated by photoabsorption, the three requisite photoirradiation. Without photoirradiation, no photoabsorption happens. So the photoirradiation is necessary, and the photocatalyst which absorb photons, that is also necessary. And of course, reaction substrate must be. So therefore, those three photoirradiation, photocatalyst, and photoirradiation, photocatalyst, and the substrate, three requisite is necessary. それはそうです。だけど、again, this is necessary condition. Even if this Planck test, you check the Planck test, and that is okay. So only the reaction happens only when those threes are there. But important point is photoreaction initiated by photoabsorption of a compound absorbed by a solid surface and the subsequent electron injection also requires three requisites. つまりこれはこのブランクテストは必要条件なので十分条件じゃないわけです。このブランクテストを満足したからといって光触媒反応かどうかわからない。で、例えば例としては光触媒と思っていた、実は光触媒じゃなかった。固体の上に吸着された基質が吸着された状態で光を吸収する。で、反応するんだ。という場合には、やっぱり3ついるんですよ。光照射はもちろん必要だし、吸着してくれる固体がないと別に起こらないし、もちろん反応基質がないと起こらないわけです。だから、このブランクテストを通ったからといって、絶対光触媒反応、つまり光触媒が光を吸収して反応を起こしているかどうかわからない。なので、それをチェックするためには、アクションスペクトラム、つまりどんな波長の光で反応したのかっていうのを調べる必要がある ということになります。いいです。で、これが一つの必要条件ですね。はい。So then, what is another necessary condition for photocatalytic reactions? The first one is the reaction must be initiated by photoabsorption over photocatalyst or a solid material to be photocatalyst. And what is another necessary condition of photocatalytic reaction? What should be checked? はい、どうぞ。光触媒が光を吸収して反応が開始するんだということをチェックする必要がある。それは一つの必要条件。もう一つ大事な必要条件あるんです。何でしょう。今までの、特に最初の方の原理のところをちゃんと聞いてれば、もう一つの必要条件わかると思います。ちょっと考えてください。はい。でしょうか。Photo absorber that should be photocatalyst remaining unchanged. つまり、光触媒っていうのは変化しちゃいけないので、それを確認する必要があるということです。だから上の条件で、ネセサリーコンディションで、ちゃんと光触媒が光吸収して反応してるっていうことが分かったとしても、その光吸収したやつが変化しちゃうと光触媒反応にならないので、それをチェックする必要があります。So it is necessary to check the photoabsorber that it should be for the catalyst remains unchanged. And to check this, checking the turnover frequency, molar ratio product to photocatalyst to be more than unit と言います。で、実際には全然変化してませんってことを本当は言わないといけないでしょうね、多分ね。でもあんまりチェックされてません。例えば参加者なんか誰もこんなことチェックしてませんけど、多分大丈夫なんだろうなってみんな思ってる。そんな感じです。で、元に戻って、この最初のフォトアブソープション。思っている光触媒がちゃんと光吸収して反応してるんだっていうことを示す方法がブランクテストです。で、そこに至る論理をちょっとお話します。The logic. So, before talking about the action spectrum, I should check that you understand the logic for this scientific studies. And it should be, if a PC is photocatalytic. If photocatalytic reaction, if that is photocatalytic reaction, and photoirradiation, solid material, photocatalyst, and substrate, the large S is substrate, must be there. もし光触媒反応であれば、光と固体である光触媒と反応基質がないと起こらない。さっきのプランクテストですよね。これ正しいです。This is true because this is kind of definition. So photocatalysis must occur only when light, solid, and substrate are there, co-present. それは当然。だけど、プランクテストは光とソリッドとサブストレートがあったらフォトキャタリシスだっていうのは、これは true です。If this is photocatalysis, the light, solid, and substrate must be there, present at the same time. So this is true. But this is converse. So therefore, it is impossible to say that, to say that even if blank test passes, it is impossible to show this is true. So this is just a necessary condition. Okay. So therefore, the killer card to exclude the possibility of this, the killer card is this one. The light and solid and substrate is necessary, but not the photocatalytic reaction. If we found such an example, for example, the dye-sensitized reaction I will talk about later. In that case, the light, solid, and substrate is necessary, but that is not a true photocatalytic reaction. So therefore, in that case, it is impossible to say this blank test. Okay, again? Okay, いいですか？これはデフィニション、定義です。フォトキャタリシスだったら光と光触媒とサブストレートの基質が必要だ。これ定義ですから、これは true です。だけど、ブランクテスト、光と固体と反応基質があるときだけ、3つが共存しているときだけ反応が起こるというブランクテストを通れば、フォトキャタリシスだっていうこの命題は、この true の命題の逆なので、逆は必ずしも真ならずということになります。そこポイントです。で、この命題が絶対にいつもtrue ではない、常に true ではないということを示すのがキラーカードで、キラーカードっていうのはそれが見つかっちゃったらもう絶対これは、true とは言えない。true の場合もあるかもしれないけど、true とは言えないというのがあって、それが光と固体と基質がいるけども、でも光触媒反応じゃない。でそれは、今から説明します色素増換反応、色素が入っている場合の反応というのはそういうことが起こりうるんですけど、それは光触媒反応じゃない。光触媒が光吸収してない。というキラーカードというわけです。で、それは見つけたんです。今から説明しますけど。だけど、見つける前からもう分かってた。これは定義で、これはその逆の命題だから常に成り立つわけではないというわけです。常に成り立つわけではないというのは単に必要条件、ネセサリーコンディションだっていうわけですね。だから別にこんなキラーカード示さなくても、ブランクテストが通ったからといって光触媒反応じゃないこともあり得るということは分かってた、論理的には。でも誰も気がついてなかった。誰もって言ったら悪いけど、 まあ、ほとんど誰も気がついてなかった。だから、結構、こんな簡単な論理はよく理解されてない場合がある。で、さっきも言ったように、これは定義です。This is the definition. If that is photocatalysis, light, solid, and substrate must be there. And this must be true because this is definition. And killer card is no light. So this underbar is not. So no light, no photocatalyst, no substrate. 光照射がなくて、ソリッドが入ってない、あるいは基質がない。これいずれかですね。これはオアで。いずれか欠けてるときで、なおかつ光触媒反応が起こっているっていうのがキラーカードなんですけど、これはありえないわけです。これが定義ですから。だから、このキラーカードは存在しない。でこれだから常にトゥルーなんです。ここは大事なポイントです。So then, what I'm talking today is action spectrum analysis to say the visible light responsible photocatalyst. So because the titanium is white, means no visible absorption, only absorbing ultraviolet light. So therefore, the titanium is white. Yes. So then that is not so good because so many visible light, much visible light in solar radiation and the ordinary light source. So therefore, utilize those visible light is important. So therefore, many numerous numbers. So impossible to measure the number. So many people want to make titanium to visible light active photocatalyst. And so to do so, the titanium must have some color. And it is not so difficult to make titanium with colored titanium. But this cannot be directly said that is the visible light responsible titanium. So to make titanium, the visible light responsible titanium, it is necessary to give color to titanium. This is only one necessary condition. So therefore, even if the titanium has color, that cannot be responsible for visible light. So this is very easy logic that many people misunderstand. By making titanium, the colored titanium, it is possible to develop the titanium responsible for visible light. So visible light induced photocatalysis, true photocatalysis, that requires visible light photoabsorption. Yes, this is true, every time true. But if the titanium has visible light absorption, that gives the visible light induced photocatalytic reaction. This is converse. So this is true, but this is converse. So therefore, it is impossible to say that is always true. It's possible to determine true or false. 可視光で光触媒反応が起こるという場合には当たり前だけど、光触媒は可視光を吸収しないといけない。これ一種の定義なので、これ true です。真です。いつでも。この命題は常に真。だけど、色のついた光触媒と思わしきものが作れたら、それが、可視光で光触媒作用を示すんだという命題は、この命題のコンバースですから、逆は必ずしも真にならず。なので、いくら可視光吸収のあるやつ作ったとしても、それは どうかわからない。で、当たり前だけど、キラーカードは、光、可視光吸収がないのに、ない光、可視光化の光触媒反応っていうキラーカードなんですけど、それはない。それはない。これは定義でないので、このキラーカードは存在しない。これは絶対常に true なんですよ。でも、これに対してはキラーカードはいくらでも存在です。で、アクションスペクトラム、サイズスペクトラムです。Then, the action spectrum. That is measurement of something. So, in almost all the cases, the apparent quantum efficiency. So, do you remember the difference of quantum efficiency and the apparent quantum efficiency? That is, apparent quantum efficiency is the efficiency of reaction induced by incident divided by incident photon flux. And quantum efficiency, true quantum efficiency is the reaction rate divided by absorbed photons. For apparent quantum efficiency, that is not absorbed, that is incident photons. 量子効率と見かけの量子効率の違い、覚えてます？アパラントカンタムエフィシエンス、見かけの量子効率というのは、入射光に対する反応速度です。で、カンタムエフィシエンシー、量子効率、真の量子効率というのは、吸収量に対する反応速度。ちょっと違うんですね。入ってきた光を元にします。で、いろんな波長の単色光って言いますけど、単色光、特定の波長の光を当てて反応して、レスポンス、大概はアパラントカンタムエフィシエンスにしてプロットするということをやるわけです。で、もう一遍復習すると、カンタムエフィシエンシー、あるいはカンタムイールドと言いますけど、カンタムエフィシエンシーというのは、もともとの均一系の光反応の定義は、こうでした。だけど実際には光触媒反応ではそれが使えないので、実際には、absorbed photon flux と反応に使われたphoto induced generated the whole positive hole and electrons, the rate of reaction of those. And for apparent efficiency, so that is incident photon, not that are coming to the reaction system. And in that case, only I is used. For real, a true quantum efficiency, I5 is used. And it is necessary to assume the number of electron and positive holes to be used in photo reaction. This is just an assumption. No way to determine the number, actually. And for example, for acetic acid decomposition, if that is measured in the amount of carbon dioxide, that is 4 mole of photons is necessary to produce one carbon dioxide and something. And by using those assumptions, it is possible to analyze the apparent quantum efficiency. So then, if the photocatalyst absorb light, something like this, that is wavelength dependent, that is photoabsorption efficiency. And actually, you know that at the higher wavelength, the energy is small, and it is impossible to induce the excitation from valence band to conduction band. So therefore, no efficiency, zero. That means no absorption in visible range for titanium. And this is increasing in UV region. And if the quantum efficiency. Quantum efficiency is quantum efficiency, absorbed. So the number of photons absorbed using this, the reaction rate, number of molecules is divided. And then if that is the same. So actually it is possible to assume this, the constant quantum efficiency, not depending on wavelengths. That is every time, even if the different wavelengths absorption is made, and that means the position of electron in conduction band and the positive hole in valence band is different. That is relaxed to conduction band bottom or valence band top position. So that means the ability of those electron and positive hole are the same. So therefore, quantum efficiency, real quantum efficiency can be constant. In such case, the action spectrum, the result, the apparent quantum efficiency can be like this. The shape is the same as photoabsorption spectrum because the quantum efficiency is constant. And if the quantum efficiency is different, that means the longer the wavelengths, the higher the efficiency. In that case, this absorption spectrum is shifted to longer wavelength side in action spectrum. Okay, and assuming the constant quantum efficiency, not depending on wavelengths, when we obtain the action spectrum similar to the photoabsorption spectrum, it is possible to say the photocatalyst or material absorbing this drives for the catalytic reaction. And the action spectrum resemble is similar to the photoabsorption spectrum titania. It is possible to conclude titania absorb the light to induce this reaction. This is the action spectrum. And my first example, probably at that time in 1985, that is the first year of my assistant professor, research associate position. And at that time, I thought that this is the first example of action spectrum of photocatalysis, but actually, at least in 1971, already the titania action spectrum has been already reported. Anyway, the apparent quantum efficiency is plotted against wavelengths. And this dashed line is the photoabsorption spectrum of titania in suspension. And it is possible to conclude that this reaction, that is a hydrogen evolution from 2-propanol solution, can be induced by photoabsorption by titanium. So this is true, but this is not so interesting. This is must be natural. And after that, we checked again the action spectrum of photocatalysis, and this is the second graduate student of environmental science。第2期生、中村さんっていう人ですけど、がやりました。This is a xenon lamp, and here is a mirror, and introduced to the monochrometer, 分光器ですね。で、ここに資料を入れて反応させるわけです。これ今もそれまで、so in the ordinary case, the photocatalytic reaction is operated by using the mercury arc that is very intense, very high intensity lamp. But actually, this monochromatic light from this monochrometer is about 0.1 milliwatt. So that is so low. If ordinary mercury arc at 365 nanometer is about 20 or 30 milliwatt. that is 2 orders of magnitude higher than this. And that is very, very low intensity light. So therefore, one reaction requires 1 day. And 1 week, only 5 wavelengths can be measured. です。ものすごい弱い光なので、1日に1個の波長しか測定できない。1週間で、まあ、その土曜日にデータ解析するとしても、1週間で5点しか取れないんですね。アクションスペクトルも5点では1個のアクションスペクトルにならないんですけど、まあ、それをかなり頑張った。で、その後、もうちょっと、まあ、研究経費が、ついたので、もうちょっといいやつを買いました。これは11点。11 sample with different wavelengths can be analyzed at the same time. And the intensity is very high, 0.1 to 18 milliwatt square centimeter, and with high FWHM, full width at half maximum. 半地幅も非常に、まあ、狭い20ナノメーター。まあ、分光器としてはあんまり良くないですけど、まあ、照射の波長としては十分なもので、同時に11点測定できる。11個の違う波長の光を同時に当てられる。まあ、実際には5個ぐらいですけど、当てられるという優れもので、まあ、これはかなり飛躍的に良くなりました。で、これを使って、最初に測定したのが、メチレンブルーの話でした。で、メチレンブルー、so this is published in 2006. And at that time already, so many papers claim that the methylene blue is a good substrate to check the photocatalytic reaction. メチレンブルーというのは色素ですから、非常に簡単に測定できます。まあ、色がなくなるので測定できる。で、それを使って光触媒活性が、メチレンブルー、まあ、使って、メチレンブルーっていうわけですが、青い色。これ赤い光吸収するから青い色の色素なんですけど。で、それでたくさんレポート出てたんですけど、そのアクションスペクトルを取ってみた。とんでもないことだったってことが分かりました。で、それはどういうことかっていうと、これが結果で、これは九州工業大学の大野先生との共同研究なんですけど、大野先生とここで作った硫黄ドープ酸化資産。それから P25、これは普通の酸化資産です。So P25 is a very famous commercial titanium oxide, and this is white. And the Professor Ono in Kyushu Institute of Technology prepared a sulfur-doped titanium absorbing visible light. So this is the absorption spectrum, and the absorption is extended to 600 nanometer. So that is yellow color. So blue part is mainly absorbed by this. So this is a visible light absorbing titanium, but not yet proved that is visible light activity. And the methylene blue, that is the dye, blue colored dye. That means the absorbing the red part mainly. So therefore the blue color remains. So therefore that seems blue. Yes. And this white open square is the action spectrum of P25. So the change of absorption of methylene blue in solution suspension is decreased. And here, nothing. So that means only UV light is absorbed by P25. And the sulfur of the titanium has absorption, but actually at this wavelength, not so much. And important point is here is something. So in this region, 600 to 700 nanometer, both P25 and the sulfur-doped titanium doesn't absorb light. But here is action spectrum. So some methylene blue is decomposed at this wavelength. And this wavelength is similar to the absorption of methylene blue itself. And by expanding this, this might be. And in this region, no absorption for both sulfur-doped titanium and P25. But actually, methylene blue is decreased by photoirradiation. So, important point is without titanium oxide, no such decrease in concentration of methylene blue is observed. So that is blank test has been passed in all the cases. And important point is for sulfur-doped titanium, here is some new peak in action spectrum. So this can be, but at the same time, the methylene blue in suspension has absorption in this region. So therefore, it is impossible to conclude the sulfur-doped titanium has visible light activity in this region. 硫ドープの酸化資産も P25 もどちらもこの600から700の領域でメシルンブルーの減少が見られました。この領域ではサルファドープ、硫ドープの酸化資産も P25 も吸収ありません。だけどメシルンブルーは減少するわけです。だからこれも明らかに酸化資産によるものではないということは分かります。それから硫ドープの酸化資産だけこの領域にアクションスペクトラムを示すんですけど、この領域でもメシルンブルーなくて P25 はだからここはひょっとしたらサルファドープの作用かもしれませんけど、でも全部じゃない。この長い波長の方は、これは絶対に酸化資産の吸収ではありません。というわけです。で、そこで、酢酸 ACOH っていうのは酢酸です。ACOH is acetic acid. So, acetic acid decomposition is also examined. The acetic acid solution has no visible light absorption. So, therefore, no direct reaction happened. And for sulfur-doped titanium and P25 and expanded in this region. Actually, sulfur-doped titanium has action spectrum expanded to 600 nanometers. That is almost the same as photoabsorption of sulfur-doped. Yes. So therefore, it is possible to conclude sulfur-doped titanium can absorb this visible light region, even though the quantum efficiency is not so high. This drives the photoabsorption in visible light, drives the decomposition of acetic acid, and this is true photocatalytic reaction. So by checking this action spectrum, it is possible to say that. Okay, so the time is over, and I will interpret this part again. And at the last, when we submitted this paper, the Yan-san from China performed all the experiment, and I told her that this paper can be published, but it is impossible to expect the high citation, because if someone wants to use methylene blue, they don't like to cite this paper. And if someone don't use methylene blue, no need to cite paper. So therefore, it is impossible to expect the high citation of this paper. But actually, so many papers cite this paper. And part of them clearly report the methylene blue decomposition, not the photocatalytic reaction, but they reported that is photocatalysis. So the problem is, this is question. A title is methylene blue an appropriate substrate for photocatalytic activity test? So those misunderstanding may happen to understand this is the answer is yes. はい。これ最初にこのペーパー、投稿するときに主にやってくれたヤンさんっていう博士研究員の人に、これはあんまり引用は期待できない。メチレンブルー使う人はこんな引用したら困るし、メチレンブルー使わない人は引用する必要ないから、誰も引用しないんじゃないかって、実際にはかなり引用されて、で今で もう20年近く経ってますけど、もう300回以上引用されてるんですけど、多分半分ぐらいはメチレンブルーを使った研究です。最初の100歩出た時に半分ぐらいそうです。だからこれは読んでないんですよ、中を。このタイトルが疑問形で、適切かっていうのをイエスだと思って引用してるんだと思いますけど、まあだから論文の引用数なんで大したことないですね。はい。今日は以上です。いつもの通り72時間以内にメールを送ってください。今日は PC2022-0616 です。はい。はい、お疲れ様でした。また、では来週お会いしましょう。以上です。